Good morning. So yesterday we have discussed about the effect of zeta on the second order performance and the second order system's performance. Effect of zeta for the zeta of greater than 1 we have discussed, and the zeta is equal to 1 we have discussed, and zeta is less than 1, it is 0 is less than 1 we also discussed. And today we discuss about the zeta is equal to 0. So these are the 4 cases which we have, and each case we have discussed here. For the zeta is greater than 1, we have told that it is a purely exponential behavior, and also zeta is equal to 1. Zeta is equal to 1. We have discussed that it is a exponential but critically damped exponential behavior and critically damped. And for zeta is less than 1, we have discussed it is having a oscillatory behavior. We have discussed, see, if you look at the previous class, so this is the output equation which you have the response equation, that is C of t. C of t is equal to CSS plus some constant into e power minus zeta omega n into t sine of in bracket omega into root of 1 minus zeta square into t plus theta, right? So here this is represents, this sine term represents sine, there is a oscillating behavior, but that oscillating behavior will be means with a reduced amplitude. Why there is a reduction in the amplitude? In the sense, because of this negative exponential term, there is a reduction in the amplitude. So that is the curve. Say for example, the curve is moving like this and then reaching it. So this oscillating behavior is reducing its amplitude. So see, this is what. So as the because of this how it is reducing, because of this exponential negative exponential term, as the t tends to infinity, this term equal to 0, so that is why this sine term will goes off, and as I told that the reduced amplitude, so this frequency we can call it as damped oscillation. We can say damped oscillations or damped frequency oscillations, which we can write omega d is equal to omega n into root of 1 minus zeta square. So this is what we can say damped oscillations or damped frequency of oscillations. So that is why there is a reduction in the amplitude. So that is why we can call it as damped oscillations or damped frequency of oscillations, which can be represented as omega d. D stands for damped oscillation and n stands for natural frequency. Omega d equal to omega n into root of 1 minus zeta square. So this is what we have learned in the last class. So now we'll move on to the next. So today we discuss about when the case zeta is equal to 0. Fourth case 4, when zeta is equal to 0. So we have the equation C of s is equal to omega n square divided by s square plus 2 zeta omega n into s plus omega n square. So if the zeta is equal to 0, then this term will not be there. So this will become omega n square divided by s square plus omega n square. So this, if I factorize this, I'm going to get using the partial fractions. So C of s I can write as a by s plus bs plus c divided by s square plus omega n square. So if I apply the partial fractions to this equation, then I can get C of s is equal to steady state value or a. I'm going to get a plus a constant. Here there will not be any exponential term in the previous case, omega n into t plus theta. So here, if you look at this equation, if you look at this equation, this completely shows that it is a sine term. There is no exponential term. As the t tends to infinity, this sine wave will be keep present. Sine wave will be keep present. So it means that it has a constant amplitude of oscillations. It has a constant amplitude of oscillations as long as t keeps increasing. As the t increases, it has the behavior of this constant amplitude oscillations component. So this is purely oscillating behavior. This is a purely oscillating behavior. Okay, so as the zeta is equal to 0 means there is no damping. So no damping. Zeta is the factor which talks about the damping. So when zeta is equal to 0, I have not provided any damping. So when there is no damping, the systems operates with a constant amplitude of oscillations. Okay, so that is why these systems are called as undamped systems. Undamped systems. So this is about the damping ratio, effect of this damping ratio on the second order system performance. That's what we have studied now. So now moving to this, the four which I have discussed now will be represented in a tabular format. See, case 1. So we have talked about the different cases, that is zeta is greater than 1. First case is zeta is greater than 1. So when the zeta is greater than 1, I mean the system what we call as this kind of systems, because over damped, because zeta is greater than 1, so those kind of systems are called as over damped systems. Over damped systems. Okay. So and the closed loop poles which you got is, in the closed loop poles we have got real, okay, unequal, real, unequal, and negative poles which have got while finding the roots of the equations. Similarly, if you look at the nature of output, the output equation, the response equation, the nature of a response equation, if you find, okay, so here it is going, as the zeta is greater than 1, it is pure, I mean which you got purely exponential in nature, right? Purely exponential in nature. That's what we have shown in the last class. The behavior of the response purely exponential as the zeta is greater than 1, because it is over damped. So it is highly damped system. So there will not be any oscillating behavior present in the output of the system. So second one, which you have discussed about the zeta is equal to 1. So zeta is equal to 1, which you can call it as critically damped systems. We can call it as critically damped systems. And what kind of roots we got in the case of zeta is equal to 1? We got the real and equal, of course, negative roots which you got. But in the previous case it is unequal roots which you got, and now in this case it is equal roots which you have got. And the behavior, the response, the nature of the response, if you look at, it is a critical and pure exponential. Critical and pure exponential. This is also exponential in nature compared to this zeta is greater than 1, but it is in a critical nature, because when it's try to reduce the zeta is equal to zeta is less than 1, it leads to the complex conjugate roots. That's why it's called critical damped systems, critically damped systems. Now moving to the third one, which is zeta is less than 1, or of course 0 is less than zeta or less than 1. Okay, so in this case we can say under damped systems. We can call it as under, because zeta is less than 1, so we can call it as under damped systems. Under damped systems, and the roots which you have got as damped, I mean complex conjugates. When zeta is less than 1, that square root term will become negative. That's why the roots, closed loop poles which you got is complex conjugates with negative part, the negative real part. Okay, the negative real part. Okay, then the nature of response, nature of response in this case is going to be, we have a sine term present in the equation, so it is said to be damped oscillations will be there. So oscillating behavior is there. Oscillating behavior is there. So damped oscillations in the sense where there is a reduced amplitude will be present in this oscillating behavior. So the oscillating behavior after some time it will be vanished. That is why it is damped oscillations. And the fourth one, so zeta is equal to 0 means no damping. So it is called no damping or undamped. Undamped systems. We can call it as undamped systems. So whereas just now we found that the roots of this is going to be a purely imaginary which you got. So if you look at this equation, purely imaginary roots we are going to get in this case of closed loop poles. And the nature of response curve. So it is a, as we told that it is a constant amplitude we are going to get. So oscillations will be present. Oscillations will be there with the constant frequency, because constant amplitude we are going to get the oscillating behavior of the system. So oscillations with the constant frequency and amplitude, constant frequency and amplitude. So these are the 4 different cases and their behavior and their closed loop poles and what you call those kind of systems. So here in your syllabus we have underdamped case. This one we have. So this we are going to study in detail for the different inputs. So the effect of zeta, that is zeta is less than 1. When the zeta is less than 1, so now we are going to move to the unit step response, we can say unit step. So we are going to use the unit step input as the input. Okay, and I need to find out the response of a second order system. I need to find out response of second order system. So response of a second order system I'm going to find out. So we have discussed about the second order system. What is the response of a second order system for the different zeta values. So here, as the zeta varies, how the response of the system is going to be. So here, if I look at the input I have taken as unit step input, and I have to consider as the different zeta values. Zeta is greater than 1 we have, zeta is equal to 1 we have, zeta is equal to 0 we have, and also we have 0 less than zeta less than 1. So I am considering only one case in this this underdamped case. So considering underdamped case. Okay, so I'm going to find out, that is C of t, which you have told in this. While discussing the cases, we have told that C of t is equal to CSS plus some constant, which you have told some constant, and exponential term minus zeta omega n into t into sine omega into sine omega d t plus theta. So we are going to get this equation. So how to derive this equation? We'll discuss now. So these are the different cases. So I have considered what and all I have considered. One is unit step input. The other one is I am considering the response of a second order system, and the zeta value I have taken is less than 1. Zeta is less than 1. So that case I have taken. Now derivation will talk here. So first consider the that root, I mean denominator C of S, okay, C of S by R of S is equal to, we know that second order system, standard second order system is like this, S square plus 2 zeta omega n into S plus omega n square. So as the R of S value is, because I have taken the unit step input, so R of S will become 1 by S. Taking to that side, I'll be getting C of S is equal to omega n square divided by S into S square plus 2 zeta omega n into S plus omega n square. So once you get this equation, so I'll go for getting the roots of this particular equation. So S square plus 2 zeta omega n into S. So if I substitute less than zeta is less than 1, we have S1 comma 2, that is minus zeta omega n plus or minus root of, omega n into root of zeta square minus 1 we have. So if zeta is less than 1, then this roots will become minus zeta omega n plus or minus. So this, if I interchange this term 1 minus zeta square, then I'll get z into omega n into root of 1 minus zeta square. So these are the roots which you can get. So this root I'll take it as, rather than for every, as I'm going to substitute in this above equation, so I'll write, replace this term with a alpha is equal to zeta omega n, and this term I'm going to replace with, we know that it is a equation of damped frequency of oscillation. So I'll replace this with the omega d. So omega d is equal to omega n into root of 1 minus zeta square. So now my roots will become S1 comma 2. For our convenience, I'm replacing this word with these two terms. Now I got x plus jy form. So right. So now if I substitute this in the equation, in the above equation, substituting these roots in the above equation, we'll get C of S. This equation I'm taking, okay. So I got this way, roots of this equation, and I use the partial fractions. Say C of S is equal to, I'll say A by S plus, because it is, these roots cannot be factorized into, so partial fractions, when the roots are not factorized, then I'm going to use the Bs plus C. So Bs plus C divided by S square plus 2 zeta omega n into S plus omega n square. So this is the, for this equation, so I have written the partial fractions. So by using this partial fraction method, so I have to get the A and B and C values, okay, A and B and C values. Now omega n square divided by S into S square plus 2 zeta omega n into S plus omega n square. This is equal to, I have written as A by S. So I'll take the LCM. So A into S square plus 2 zeta omega n into S plus omega n square. Okay. So now plus S into Bs plus C whole divided by S into S square plus 2 zeta omega n into S plus omega n square. Now we need to compare the numerators. On both sides. So if I look at this, the S square coefficients. First look at the S square coefficients. What are the S square coefficients in this case? A into S square plus B into S square. So A plus B, Here, what about the s square term here? There is no s square in this case. I'll be getting a plus b is equal to 0. A plus b is equal to 0. And similarly, if I take the s coefficients is equal to here. If you look at, I have got a into 2 zeta omega n, a into 2 zeta omega n. Here is the s term, and here is the s into c, right? So c plus c. So what is the s coefficient in this left hand side numerator? Nothing is there, so I'll be keeping 0. I'll be keeping 0. And similarly, constant terms. Omega n is a natural frequency. Natural frequency for any system, it is constant. So this is a constant term. This is a constant term. So here there is no constant term. So a into omega n square is the constant on the right hand side, and on the left hand side omega n square, this is the constant term. So omega n square is the constant term. So I'll be using a into omega n square is equal to omega n square. So by cancellating this last term, so omega n square be cancelled out, then I'll get a is equal to 1. I'll get a is equal to 1. So once you got a is equal to 1, I'll get here c, right? So we know that a plus b is equal to 0. So b is equal to what? Minus 1. So 1 plus b is equal to 0. So b will become minus 1. Once you got b and a, so here substitute c is equal to what? C is equal to minus a into a is 1. A is 1. So I'll substitute here. So minus 2 zeta omega n. And also we told that zeta omega n is taken as alpha. So I'll write this as minus 2 alpha. Minus 2 alpha. Okay. So this is the values which I have got, and these values to be substituted in this equation. So in this equation, so we got the a value and we got the b value and c value. Substitute in this equation. So c of s is equal to, so that equation I'm going to substitute. So c of s is equal to, we have wrote a by s plus bs plus c divided by s square plus 2 zeta omega n into s plus omega n square. So the same, I'm substituting the values here. So c of s is equal to now 1 by s plus b is equal to minus 1 I got, so minus s, c equal to I got minus 2 alpha divided by s square plus 2 zeta omega n into s plus omega n square. So this is what we have after substitution. Of course, you can take the minus here common, and we can write directly 1 by s minus s plus 2 alpha divided by s square plus 2 zeta omega n into s plus omega n square. So this is what I can write. And also here, if you look at this zeta omega n, already we have replaced the zeta omega n with a alpha. So here is also zeta omega n. So here is in the denominator, we got the zeta omega n. So that also I can replace and write c of s is equal to 1 by s minus s plus 2 alpha divided by s square plus 2 alpha into s plus omega n square. So now, so this is the term which I have got, and we can reframe, rearrange these terms and all those, I'll be getting in the form of, say for example, s plus alpha. So c of s is equal to 1 by s minus s plus alpha. Okay, s plus alpha plus alpha, I can write s plus alpha plus alpha, okay, whole divided by s square plus 2 alpha s plus omega n square. So here I will separate the terms. I will separate the terms here. This one is one term and this one is one term. So in this way, so 1 by s minus s plus alpha by s square plus 2 alpha s plus omega n square. Okay, so and plus alpha by s square plus 2 alpha s plus omega n square. So I'll just separate terms. Next, so this s plus alpha by, if I write, if I want to write, get into the form of Laplace transformation, because I need to apply the inverse Laplace transformation to get the time domain. So here it is in the form of s plus a. So here also I have to get in the form of s plus a. So, but it is in the second order. So I'll write in the whole square form. I'll write in the whole square form, that is 1 by s minus s plus alpha divided by, here I'll write s plus alpha whole square. Okay, and I mean s square plus 2 alpha s. If I want to write 2 alpha s, okay, I'll first show. I will get in the form of s square plus, if I want to write s square plus 2 alpha plus into alpha square, right? So s square plus 2 alpha s plus 2ab, a square plus 2ab plus b square. So b square is nothing but here is alpha square, right? Plus omega n square. Because I'm adding the alpha square to this equation, I have to subtract the alpha square and right. Okay, so this is the one, and then plus alpha by I'm writing similar fashion to this in the whole square form, that is s square plus 2 alpha s plus alpha square plus omega n square minus alpha square. Because I'm adding here, so I'm adding this term alpha square and I'm subtracting the same term so that it will not affect on the original equation. So here also alpha square is added and then subtracted so that it will not be affect the original equation. Why I am writing this? Because I can get into a whole square form. I can get into a whole square form. Now this is equal to, so 1 by s minus s plus alpha divided by s plus alpha whole square, because this whole thing a square plus 2ab plus b square form it is there. So I can write s plus alpha whole square plus, here we know that omega n square minus alpha square is nothing but, see, alpha is equal to zeta omega n. So alpha square is equal to zeta square into omega n square. So here zeta square into omega n square I can write. So if I okay, in the next step we'll do plus, similarly I'll write in the same fashion for this, s plus alpha whole square plus omega n square minus zeta square into omega n square, right? So now 1 by s, and here see, if you look at omega n square, if I take and count, so omega n square and 1 minus zeta square I. So we know that omega d is equal to omega n into root of 1 minus zeta square. So if I squaring on both sides, omega d square is equal to omega n square into 1 minus zeta square. So directly I can write here s plus alpha by s plus alpha whole square plus this whole term which I have written here, this whole term. Okay, this whole term is nothing but this value, right? See here. So that is why I can use omega d square in this case, omega d square in this case. So omega d square plus alpha by, similarly s plus alpha whole square plus omega d square. I can write like this, right? So I brought into the form of, okay, still I have not got into, because see, if I have a sin omega t or cos omega t, see, cos omega t Laplace transformation of cos at, I can say cos at is equal to s by s square plus a square. Similarly, Laplace transformation of sin at, we get a by s square plus a square. Okay, if I have the multiplication property of e power minus at in this case, then I'll be getting s plus a by s plus a whole square plus b square. Okay, if I have the Laplace transformation, see if I use one more. So if I have Laplace transformation of e power minus at cos bt, so this is s plus a by s plus a whole square plus b square. Similarly, Laplace transformation of e power minus at into sine bt if I have, then it will be s plus a by a by you'll be getting a by s plus a whole square plus b square I'm going to get. B square I'm going to get. So this is what we have the equation. We have the equation. So in this, if I apply, so this is b by a square plus s plus a whole square plus b square. Okay. So here it is I have to brought into this kind of form so that I can apply the L inverse of this, L inverse of this. Then I'll get the cos 80 or sin 80 or e power minus 80, whatever it is. So that is why I have to get in this form. Then only I can write the L inverse equations so that it will be suitable for this formula, suitable for this form. So that is why I have rearranged the terms from the beginning to get into this form, Now you look at, so 1 by s. This one is okay because this is in the form of s plus a by s plus a whole square plus b square. So this I can write. But here is b. Here it is s plus a by it is there. So but it has to get to b by s plus a whole square plus b square. So in order to get that one, so I have to multiply this with omega d and divide with the omega d. So what will happen? So s plus alpha divided by s plus alpha whole square plus omega d square plus, so this here I'll multiply it and divide. So alpha by omega d and omega d by s plus alpha whole square plus omega d square. Now you look at this sine form, sine b form. So sine e power minus 80 sine bt is equal to b by s plus a whole square plus b square. So it is in the form of b by s plus a whole square plus b square. So I can apply this is a constant. This is a constant. So if I apply the inverse Laplace transformation for this equation, I'll be getting in the form of these equations, that is e power minus 80 or e power minus sine bt like that. So now our equation is c of s. This is the c of s equation. Applying the inverse Laplace transformation. So applying the inverse Laplace transformation. Apply the inverse Laplace transformation. Applying the Laplace transformation, inverse Laplace transformation. That is L inverse of, means I am converting this frequency domain into a time domain. So L inverse of 1 by s, okay, minus L inverse of s plus alpha by s plus alpha whole square plus omega d square. Then plus, and of course minus into plus minus, it will become, so minus, or I can use the bracket itself for these two terms, or I can apply here plus. So L inverse of alpha by omega d is a constant, so I'll write separately alpha by omega d outside, and then omega d by s plus alpha whole square plus omega d square, right? So this equation after applying this inverse Laplace transformation, so L inverse of 1 by s is 1, because we know that Laplace transformation of 1 is 1 by s. Laplace transformation of, see if I write Laplace transformation of 1 is 1 by s. So if I apply the L inverse of 1 by s is equal to 1. Similar way, C of s will become C of t, because Laplace transformation of f of t is equal to f of s. So L inverse of f of s will become f of t, like that, C of t. and L inverse of 1 by s is 1 minus, this is in the form of s plus a by s plus a whole square plus omega. So this is the property of this minus e exponential multiplied by exponential term. So I can write e power minus at minus a is what? Alpha into t, then cos dt. What is the b here? Omega dt. So cos omega d into t. Then this is in bracket, right? So plus alpha by omega d into, this is in the form of b by s plus a whole square plus b square. So this can be written as e power minus at, that is minus alpha into t. Then sine bt, sine omega d into t. So this is what we got. Now from this equation c of t, which is equal to, see, I have taken the common e power minus alpha. You can take the common e power minus alpha outside. 1 minus of e power minus alpha t. Okay, this is cos omega d into t plus alpha by omega d into sine omega d into t. Now if you look at in the above equation, we substitute alpha value and zeta, omega d value, then I'll get c of t is equal to 1 minus of e power minus zeta omega n into t cos of omega d. We know that omega dt, I'll keep like that only. This omega d will substitute omega dt. Alpha is zeta omega n, and this omega d is omega n into root of 1 minus zeta square. So, and the sine omega d t. So here these two terms will be cancelled out, that is omega n and omega n. So we can get c of t is equal to 1 minus of e power minus zeta omega n t, and if I take the LCM, I'll be getting root of 1 minus zeta square outside, and here root of 1 minus zeta square into cos omega dt plus zeta into sine omega dt. Right. So here, if I get this form in this sine term, okay. Yeah. So c of t is equal to, see here, I know that sine a plus b, sine of a plus b is equal to sine a cos b plus cos a sine b. So here I'll write, this is the b, okay, so cos b, and this is in the form of, say, sine a plus cos a sine b. Okay, so if I write in this form, comparing with this, we can write the sine theta as, I can write as sine a plus b, means sine omega dt plus theta. I can write as omega, a is omega dt and plus theta. So if I compare those terms, I'll be getting the sine theta is root of 1 minus zeta square. Okay, sine theta is, and cos theta is, we will get zeta. Cos theta is zeta, and from this we can get what? Tan theta is equal to root of 1 minus zeta square by zeta. So this is the we can get from this expression, and replacing this term with this one. So what will happen? Then c of t is equal to, 1 minus of e power minus zeta omega n into t divided by root of 1 minus zeta square. See, this root of 1 minus zeta square, I'm going to replace with the sine theta. Then cos omega d t. Okay, cos omega d t. And similarly, I can write cos theta sine omega d t. So I'll write this in the form of sine a plus b. So 1 minus of e power minus zeta omega n into t divided by root of 1 minus zeta square sine of omega dt plus theta. So this expression which have told during the discussion of effect of zeta on the second order or system performance for the case of 0 less than zeta is less than 1. So this is what he can call as the expression for the second order system response for the given unit step input and under damped case. So these are the 3 points which I have discussed, right? One is the unit step input in the beginning of the derivation. Unit step input we have taken, and a second order system which you have taken, of course, second order system. And then third one is zeta is less than 1. Under damped case we have taken. So for this case, this is the expression of response equation. Expression of response equation for any t value, we can calculate what is the this thing and all. I mean, what is the output, what is the response and all. So here. So now, so that is the expression which you have got. Now we'll calculate the important which you have obtained from the above equation, which is the equation. Important features which you can get from this. Important features which you can get is this. So C of t is equal to 1 minus e power minus zeta omega n into t by root of 1 minus zeta square into sine omega dt plus theta is the expression which you have got for the output equation. So in this case, see, this is we have taken 3 important important points before deriving this equation. One is that it is under damped case and the unit step input, and also we have considered the standard form of second order system. Suppose if the magnitude is A rather than unit step input, if I have a magnitude of A, then this expression is changes. This expression is changes A into whole thing. That is 1 minus e power minus zeta omega into t divided by root of 1 minus zeta square into sine omega dt plus theta. For which case it is when the magnitude is A units. This is magnitude is how much? 1. So this is for unit step input. This is the magnitude of A. So multiplied by A. And also here we have considered the standard form of omega n square by, if it is not in the form of omega n square plus 2 zeta omega n into s plus omega n square. So here if it is not in the numerator, is not in the form of omega n square. If it is, say for example, k by s square plus 2 zeta omega n into s plus omega n square is there. So here this has to be converted with the k by omega n square into omega n square by s square plus 2 zeta omega n into s plus omega n square. Now this shows the standard form. So here the multiplier is k by omega n square. So C of t, in this case it will become k by omega n square. K by omega n means before writing this equation, I can write k by omega n square 1 minus of, as it is with the zeta omega n into t divided by root of 1 minus zeta square into sine of omega dt plus theta. See, this is for when the numerator does not contain the omega n square in the second order system. So these are the important points which you have derived from this equation. Now we'll move on to the transient response specifications. That is these derivations are very important. Today what I have discussed and what I am going to discuss now also. Okay. Transient response specifications. Transient response specification. Okay. So what is it? Of course, we know that what is the transient response. So if I draw a transient response in a oscillating behavior, of course, the example which I have taken is oscillating behavior. Okay, in this oscillating behavior, we know that there is a peak. It reaches the peak value and come back, then goes to the lowest and then come back once again, and then one more second peak. Then it is coming to reach the steady state value, say for example like this. So assuming that there is a actual desired output, this is called as desired output. Say this is the desired output, means this is called 100% of the output. This is called 100% of the output. So this is the C of t on the y-axis and the time on the x-axis. Okay, so here I have as transient response specifications in the sense. So there are time domain specifications. We can call as time domain specifications. In the time domain specifications, we have the different times. See, as we told that in the previous class. So this point is the means at this particular point of it is called a steady state system. So how much time is required to reach the steady state? How much time is required to reach the steady state is called as okay, settling time. That is what we have told in the while discussing the steady state analysis. So how much time it requires to reach this steady state point? That is what you can call as settling time. Similarly, how much time required to a peak maximum value, means which you can call as peak time here. The time required to reach its maximum value of the output. That is called as peak time. And one more very importantly, rise time. Rise time is nothing but, so that is the time required to reach the 90% of the output. So that is what you can call as rise time, means from 10% to 9%. So 90%, 10% to 90%, how much time it requires to reach this output is called as rise time. Similarly, delay time in the sense, say 50% of the output. If I have a 50%, of the output, the time required to reach the 50% of the time, that is called as delay time. So these are the time domain specification which we are going to talk about. And also we have maximum peak overshoot. We can call this is called as maximum peak overshoot. That is represented in the form of MP, or sometimes percentage is also they are going to represent. And this we know that it is a steady state error. So this is what you can call as a transient response of a system which is in an oscillating behavior. Here we have a different terminologies which I have used. One is TD, TR, TP, TS, and MP. Okay, steady state error anyhow we have discussed how we can calculate, and these are the different terminologies which are used in the transient response of a system. So now we can derive these equations. So here, as I told, that delay time is TD. That is, delay time is nothing but it is the time required for the response to reach its 50% of its final value. How much time it requires to reach its 50% of its final value is called as delay time. It is the time required to reach its 50% of the final value is called as delay time. Similarly, the rise time which I have defined, that is from 10% to 90%. So it is the time required for the response to rise from 10% to 90% or 0 to 100%. You can take any way, 0 to 100% or 10% to 90%. So the rise time is nothing but It is the time required for a response. It is the time required for the response to rise from 10% of the 10% to 90% of the final value. Final value. So the rise time is we can define, of course, equations. We can derive the equations for each time, but we should know what are these terms definitions. Peak time. So it is the time required for the response to reach its final value. So this is what we can say final value, right? I mean, to reach its final, I mean, peak value, peak value. So this is the final value. So in this, while defining the peak time, so it's already reaches at this particular point of time, but still it moves up and reaches the peak value of the output, peak value of the output. So it is the time required for the response to reach its peak value. It is to reach its peak value, and also it can be defined as, time at which the response undergoes the, this is called first overshoot. It is the called as first overshoot, and this is called as first undershoot. This is called as first undershoot, and this is second overshoot, and this is second undershoot. So likewise, first overshoot, so it is also can be defined as the time at which the response undergoes the first overshoot. This is the first overshoot, right? Now, this is called as peak overshoot, which I have told, that is MP, which you can define as peak overshoot. Peak overshoot is this is the largest error. Means, see, this is the actual value which you need to get, right? But I have got at this particular point of time at this TP. So this is the error this is the largest error. This is the largest error in the system. So it is the largest error between the reference input and the actual output which you got during the transient phase. That is what you can call as peak overshoot. So it is the maximum error. It is the actual value and this is the obtained value. So this is the error which I have got at the time TP. So that peak overshoot is called as largest error. Now, so last one, that is settling time. The settling time is the time defined as the time required for the response to reach its steady state value, or that it can be defined as the time required for the response to stay within the specified percentage of final value. Means it can have plus or minus 2. This is called tolerance bond can be applied. Tolerance bond, I mean, plus or minus 2% is allowed. Say for example, plus or minus 2% or plus or minus 5%. These are called band. This is called band of the output which can be allowed. Means that plus or minus 2% error is allowed, plus or minus 5% error is allowed. So the time, this is defined as the time required for the response to decrease and as well as stay within the specified percentage of its final value, that is within the tolerance bond. So if I mention this tolerance bond like this, say for example, tolerance bond, and if this output is, yes, this is output which is in the tolerance bond, so then we can say it is reached its steady state, steady state response. It reaches to the steady state response or steady state system. So these are about the definitions of these four transient response specifications, and we can discuss the derivations in the next class. Please answer your attendance.